exactly 10:10. Yeah, okay. Uh, yes, my screen is visible right now.
Yes, sir.
Yes, sir.
Okay. Last class we discussed about the brief introduction about the semiconductors and types of semiconductors, intrinsic and extrinsic. Okay, so now we will discuss about the carrier concentration in intrinsic semiconductor. So this also I explained a little bit. So again I will revise you. Okay, so that means for finding the carrier concentration of intrinsic semiconductor. So that means here in case of intrinsic semiconductor, there are two types of charge carriers are there. We discussed already. So one is the what is that, electrons, another one is a holes. Okay, in case of intrinsic semiconductors, number of electrons is equal to the number of holes. Number of electrons is equal to number of holes. So for calculating the carrier concentration, what we have to do means we have to find out the density of the electrons as well as density of the holes. Density of the electrons plus density of the holes. Okay, just I will give little introduction about this carrier concentration. Yeah, so read. I am reading here. When a suitable form of energy is supplied to a semiconductor, then electrons take transition from valency band to conduction band. Okay, so that if you give little energy to the uh, little energy supplied to the semiconductor, what happens means, so that valency electrons jump to the conduction band. So that's why what happened here. Hence, free electrons in conduction band and simultaneously free hole in valency band is formed. Valency band is formed. This phenomena is known as electron hole pair generation. Okay, so if you give little energy to the semiconductor, what happens means, so that valency electron jump from, so that whatever the electrons in valency cell, so that jump from valency band to conduction band. If electrons are jumping from valency band to conduction band means, so in that conduction band electrons will be present simultaneously. In the valency band, holes will be formed. Holes will be formed. This phenomena, that forming of holes and generate the electrons jumping from valency band to conduction band, this total phenomenon we will call it as electron hole pair generation. Okay. In intrinsic semiconductor, the number of conduction or free electrons will be equal to the number of electron vacant sites. Number of electron vacant sites are holes in the valency band. That means here, so number of electrons in conduction band is equal to the number of holes in valency band. Okay, so this is about the, so just a brief introduction about the semiconductor, how electrons will be formed. Okay, now here suppose in conduction band, so there are so many electrons will be there at a particular temperature, so what is that energy? So that kinetic energy of the electron means, so E minus, E is the total energy minus EC gives the, so what is that, minimum energy of the conduction band, minimum energy of the conduction band. Okay, now we can also call this kinetic energy, we can also call it as effective energy of the electron. Effective energy of the electron. Okay, now coming to, similarly in case of valency band, holes will be present. So what is the kinetic energy of the hole or effective energy of the hole? Okay, so now here E is the total energy of the hole. So that means, but effective energy we want here, what is the highest energy? So EV is the highest energy of the valency band. So now EV minus E gives the kinetic energy of the hole or effective energy of the hole. Okay. Now, so this is the Fermi level here. In case of intrinsic semiconductor, Fermi level is exactly middle in between the valence band and conduction band. Okay. Now coming to the So now we will find out the density of electrons. Here we have to calculate the density of electrons as well as density of holes. Okay, first we are calculating the density of electrons. For calculating the density of electrons, what we are considering means here dn. Dn means we are taking the small volume element. Small volume element, that energy of that volume element is E and E plus dE. Okay, in that volume element, how many number of electrons will be present? Density of the electron, how much density of electrons will be present? That is the dn. That is the dn. So that dn we are calculating. Dn is equal to Z of E dE into F of E. Here Z of E dE is equal to and the energy density states. Okay, so density of states, simply we will call it as density of states. Z of E dE is equal to density of states, and F of E. F of E is the probability of electron finding. Okay, so electron occupying the energy states. Suppose if you will take one energy state, so what is the probability of electron occupied that state? Okay, so here we are taking E energy. So that means how many electrons occupied on that E energy state. E energy state, that is the probability of the electron, probability of the electron finding in that particular energy state. Okay, so now here we are taking, so total energy density. Dn means particular energy range, E and E plus dE. So but we want, so total energy is total energy density of the total density of the electrons. Total density of the electrons means here we are taking, so that means we are finding the energy density of the electron. That's why, so these free electrons, where free electrons will be present in semiconductor, intrinsic semiconductors means in conduction band. Conduction band, what free electrons will be present. Okay, what is the minimum level of conduction band here? EC, minimum energy level of the conduction band is EC. So maximum energy level is infinite. Maximum energy level is infinite. So in that total conduction band, how much? That means how many number of electrons present in a unit volume. Okay, that is the electron density. How many number of electrons present in a unit volume, that is called as electron density. We are calculating the electron density here, that is n, small n equal to, so minimum energy level is EC, maximum energy level is infinite, highest energy level of the conduction band, that is the maximum. But we don't know what is the maximum, that's why we are taking here infinite. Maximum is infinite. Okay, so this equation gives the total energy density of the electrons. Okay, simply what we have to do means we have to find out what is the Z of E and what is the F of E. Okay, if you substitute Z of E, F of E in this equation, so we can solve this equation. Now coming to the here Z of E dE. Z of E dE means energy density of the states. Energy density of the states. That means number of energy states per unit volume. Number of energy states per unit volume within the energy interval E and E plus dE. Within the energy interval E and E plus dE. Okay, so that means Z of E dE is equal to 4 pi by h cube into 2m whole power 3 by 2 into e power 1 by 2 dE. So this is the energy density states. You have to remember this value. Okay, this solution is not required for us, just we have to remember this. Okay, so now again, so if you apply this formula to the electrons here, that's why instead of m, what we are doing here, so mass of the electron, effective mass of the electron, that is the me star. Me star is the effective mass of the electron, and so energy, this is the E, this is the effective energy of the electron. What is the effective energy of the electron? E minus EC whole power 1 by 2. E minus EC whole power 1 by 2. This value we already calculated. Okay, so effective energy or kinetic energy here. So effective energy means E, total energy of the electron, minus, so EC. EC means here, so like a valency, what is that? So minimum energy of the conduction band. Minimum energy of the conduction band. This gives the effective energy of the electron. Okay, now coming to the, yeah. So that only here description is there. Okay, now coming to the Fermi level. What is the Fermi level? So Fermi level means this is the F of E, Fermi energy level here. So probability of electron occupying an energy state E is given by, so according to Fermi Dirac function, this is according to the Fermi Dirac function. So we are calculating the probability of finding the particle. So that formula equal to F of E is equal to 1 by 1 plus exponential of E minus EF by kT. Okay, this is according to the, so what is that? Fermi Dirac distribution function. Already we used previously Maxwell distribution function in quantum mechanics. Okay, Maxwell distribution function in quantum mechanics. So this is the Fermi Dirac distribution function. So that also, this also same. What is the difference between that two means? So this Fermi Dirac function is only applicable for electrons. Electrons. That means whatever the spins, spins having plus half and minus half. That particles having spins plus half and minus half. For that particles, this Fermi Dirac function is suitable. Fermi Dirac function is suitable for, so electrons, because why it will be suitable means, so electrons having their spin is plus half and minus half. For that particles, like that particles, this Fermi Dirac distribution function is suitable here. Okay, so by using this function we are calculating here probability of finding the electron. Okay, now so we will simplify this equation. So how we will simplify means, compared to thermal energy, kT is the here thermal energy, so E minus F is high. Compared to the thermal energy, E minus energy of the electron, effective energy of the electron is high. Okay, because this electron is in conduction band. Okay, that's why this that electron energy will be high. Okay, so that's why E minus EF value is very greater than kT, very greater than kT. So that's why we can neglect the one value, because in numerator this value is high, in denominator value is small. So that means this value is very high. If you will take exponential means, so this value is very high. Okay, compared to the 1. So that's why we can neglect the 1. Okay, so for large value, if you add 1 also, there is no change. There is no change, very little change. So that's why, so we can neglect the 1 here. Okay, simply we can write F of E is equal to 1 by exponential of E minus EF by kT. E minus EF by kT. Okay, now, yeah, bring this so this is in denominator. So if you bring into numerator means it will become minus. It will become minus. Okay, if you simplify it, so it will become EF minus E by kT. So this is the Fermi F of E. Okay, F of E value. Just substitute the Z of E and F of E value in the, so total density of the electrons. Density of the electrons equation. What is the density of electrons equation? N equal to integration of EC to infinity into Z of E F of E dE. Okay, substitute the Z of E value here. Okay, now substitute the F of E value here. See here. Now density of electrons N is equal to 4 pi by h cube into whatever the constant terms will be there. Write that constant terms into outside of integration. Outside of integration. Here what is the constant term? 4 pi by h cube is constant, and 2me whole power 3 by 2 is constant. Okay, and the remaining is the, so here energy is variable. Energies varies here. Okay, so that's why here we are taking E minus EC whole power 1 by 2 into integration, and exponential of EF minus E will be there. So we are simplifying this equation. For that, so I am adding and subtracting with EC. Adding and subtracting with EC. Okay, so that's why. So this equation will become, yeah. So here only variable term is energy value. E value is variable. So remaining Fermi level also constant, and EC. EC is the energy of the conduction band. That also constant. That's why we can take EF minus EC, we can write outside. Okay, so that means if you will take e power ax minus bx, e power, that means exponential of ax minus bx. How we can write e power ax into e power minus bx, we can write now. Same formula I am applying here. So this term I am writing into EF minus EC, EF minus EC into here minus E plus EC, exponential of EF minus EC into exponential of minus E plus EC I am writing. Okay, so that's here EF minus EC I am taking common out. Okay, what is the remaining term? So exponential of minus E into minus, if I am taking minus common here, so minus into E minus EC by KT. Okay, so remaining all terms as usual. So only I am splitting this term. I am splitting this term. How I am splitting means E minus EC I am taking out, because how we can take means exponential of a power x minus b bx, exponential of ax minus bx. How we can write means exponential of ax into exponential of minus bx we can write. Based on that formula, I am splitting this equation into two parts. One part is exponential of ef minus ec by kt, another part is exponential of minus e minus ec by kt. Okay, so one part I am taking common out, so remaining part will be here. Okay, so now this is the integration here. So I am doing this integration here. So for that I am taking E minus EC is equal to X for simplifying this equation. For simplifying this equation here, so I am taking E minus EX is equal to X. Similarly, here also E minus EX will be there. I am substituting here also E minus EX. Okay, this DE also we have to convert into in terms of x. This limits also we have to convert. Okay, how the conversion I will explain you. Here I am taking E minus EC equal to x. We differentiate in both sides. Differentiate in both sides means, so EC value is constant. That's why, so DE is equal to, so for differentiation of constant value is 0. So that equal to dx. So that means instead of DE we can write dx. And one more, lower limit. What is the lower limit? So lower limit is EC. Lower limit is EC. Okay, so EC means here, so we can convert, so we can take, yeah, if you substitute in this equation instead of E, so if you substitute the EC value, if you instead of E, if you substitute the EC value, so what happen? X will become, X tends to 0. Okay, if E tends to EC, so lower limit is EC. That means E belongs to EC. E belongs to EC means, so what happened? X belongs to 0. So now what is the upper limit? Upper limit is infinite. If E belongs to, energy belongs to infinite. Energy belongs to, instead of E, we are substituting infinite. So X also tends to infinite. X also tends to infinite. In that infinite value, if you remove the small value also, there is no change. So that's why X tends to infinity. Okay. So that means here, if you will take instead of E minus EC is equal to X, so lower limit will become X equals 0, upper limit will become infinite. Okay, so now substitute these all values in the above equation. Yeah, lower limit is 0, upper limit is infinite. Instead of E minus EC, E minus EC is equal to X I am substituting. Okay, here also E minus EC is equal to X I am substituting. Okay. Now, if you substitute all values here, so instead of dE, I am substituting dx. Okay. Now, this equation will become 0 to infinite into x power 1 by 2 into exponential of minus x by kt into dx. X by kt into dx. Okay. So, this equation, how it will be? So, 0 to infinity into x power 1 by 2 into exponential of minus ax dx. So, same form, like this form, above equation will be in this form. So solution of this integration equal to root pi by 2a power 3 by 2. 2a power 3 by 2. Root pi means how we can write pi power 1 by 2. Here a power 3 by 2. Instead of what is that a here? So 1 by kt is equal to a. 1 by kt equal to a. Okay. Now, So substitute this formula. Substitute this formula in above equation. Yeah. So if we substitute this formula in above equation, so instead of a, what we are taking here 1 by kt. So 1 by kt means 1 by kt whole power 3 by 2. So this is 1 by kt. It is in denominator. If it will come to numerator means it will become kt. 1 by kt in denominator actually. So if it will come into numerator means it will be kt. Okay, kt whole power 3 by 2 into, so root pi, that means pi power 1 by 2 by 2 by 2. So substitute this value in, so this equation. Okay, now simply, so down density of electrons n equal to 4 pi by h cube into 2me whole power 3 by 2 into exponential of ef minus ec by kt. So this total is constant, and now so that integration of above term here I am substituting, so this value only. So kt power 3 by 2 into root pi by 2, here. So this is 3 by 2. Okay, I am simplifying this total equation here. So here pi will be there. So pi will be there. Here pi power 1 by 2 is there. So pi into, so pi power 1 by 2. So we can write pi power 3 by 2. Okay, and here 2 will be there. Here 4 will be there. So 2 1s are 2, 2s are 4. Okay, that's why remaining term is 2 here. Okay, now whatever the so equal power terms I am writing at one place. So 2me is the whole power 3 by 2 is there. So 2me I wrote, and pi. So pi equal to here pi power 1 by 2. So pi into pi power 1 by 2. So how we can write? So pi power 3 by 2. So pi power 3 by 2. That's why I am writing here pi power 3 by 2. And where is one more term is there here, kt power 3 by 2. That's why I wrote here kt. Okay, this so total having same power 3 by 2. And here, so in denominator here h cube will be there. H cube means how we can write means h square whole power 3 by 2. H square whole power 3 by 2. So if you write like that means that 2 gets cancelled, only h cube will be remaining. So that's why, so instead of h cube I am writing h square whole power 3 by 2. H square whole power 3 by 2. So that's why this total term having same power. So I am writing this is same like that. Okay, remaining, whatever remaining will be there. So here remaining term is exponential of minus ec by, sorry, I am taking minus common here, ec minus ef by kt. Okay, this equation represents the number of electrons per unit volume in the conduction band of intrinsic semiconductor. Number of electrons per unit volume. What is the meaning of number of electrons per unit volume? Electron density of the electron density in conduction band. So this is about the electron density. Okay, so this total term, this term is constant. The term is constant. Instead of that so this 2 into total term will be there. So that constant, instead of that constant value, I am taking simply nc. So nc is the effective density of the states. Okay, so I am taking instead of this total, so nc into exponential of minus ec minus ef by kt. Okay, so this is the density of electrons in conduction band. Okay, now we are calculating the, 1 minute here. Yeah, now we are calculating the density of holes. Okay, same. So whatever doing in case of density of electrons, same we are doing in the density of holes, same procedure. So what is the difference means, so instead of previously we are taking in conduction band, now so where holes will be present? In valency band. Okay, that's why what we are taking, so we are taking the limits of the valency band. What is the limits of the valency band? What is the lower limit of valency band? Lower limit we don't know. What is the lower limit? Okay, lower limit will be, we are taking minus infinity. What is the upper limit of valency band? So what is the highest energy of the valency band means EV. That is the upper limit of the valency band. Okay, now same formula what we are doing here, that dp is equal to density of holes in the energy range E and E plus dE. in the energy range. So how much density of the electrons will be present? That is the dp. Dp is equal z of e dE into 1 minus f of e. Okay, now so total density of the electrons. Total density of the electrons means we have to integrate the total band, total valency band. How many holes will be present? How many number of holes will be present in a unit volume? We can calculate it if you integrate it. Okay, that's why I am integrating with so minus infinite to EV, highest energy. Okay, that is Z of E into 1 minus F of E dE. So why we are taking here 1 minus F of E? Okay, so F of E means probability of finding the electron. Probability of finding the electron. So but hole is nothing but so just vacant site of electron. Vacant site of electrons. So that means here how many electrons will be present in the conduction band, that much holes will be present in the whole valency band. That's why we are taking. So then what is the probability of finding the hole? Probability of finding the hole, instead of f of e, what we are doing, 1 minus f of e. 1 minus f of e, because holes are nothing but vacant sites of electrons. If electron is removed from that site, what happen, one vacant will be present, that is we will consider as a hole. That's why, so what we are taking, so f of e is nothing but probability of finding the electron. 1 minus f of e is nothing but probability of finding the hole. That's why instead of f of e, what we are taking here, 1 minus f of e. Okay, now yeah, see here, so z of e d same value. So same here, so 4 pi by h cube into 2m whole power 3 by 2 into e power 1 by 2. So if you apply the this formula for hole, if you apply the this formula for hole, so here instead of m we are taking mh, instead of m. So mh is the mass of the hole, mass of the hole, and e is the energy of the here. Yes, who is that? J6. J6, what are you doing? Why are you making noise?
Sorry, sir.
Okay, so mute yourself. Yeah. Now we are going to the class. Okay. Now Z of E dE is equal to 4 pi by h cube into same. This formula is simply applicable for the whole. Okay, instead of m we are substituting the mh. That is the mass of the whole, and this is the effective energy of the whole. What is the effective energy of the whole? So ev minus e, ev minus e, that is the kinetic energy of the whole also. Okay, so ev minus e we are substituting here. Okay, if you substitute this value, this is the z of e dE. Now, so we are calculating the here 1 minus f of e. What is the 1 minus f of e value? We know that f of e value also we know that. So what is the f of e function? So 1 by 1 plus exponential of e minus ef by kt. Okay, simply what we are doing means here 1 minus f of e. Okay, for that what we are doing means here e minus ef value. Okay, so previously what we are taking, ec minus ef, ec minus ef, sorry, e minus ec we are taking, e minus ec we are taking previously. So that value is greater than kt, because that electron is in conduction band. So if electron will be there in conduction band means that energy is high, that energy is high here. Okay, now here this e minus ef value is small, e minus ef value is small compared to the kt, compared to the kt. So that's why this total value will become small here. Okay, now what we are doing means for that, for simplifying this, so 1 by 1 plus x, 1 by 1 plus x formula this is. So that means how we can write this formula means, so 1 plus x whole power minus 1, expansion of 1 plus x minus 1, 1 plus x minus 1, expansion of 1 plus x minus 1 mean, what is the expansion means, 1 minus x plus x square minus x cube, like that it will be. Okay, so this value will be small, we are considering here. So because e minus ef value is smaller than the kt, smaller than the kt, that's why this value is small, this value is small means the exponential of this value is very small. So that's why higher order terms of smaller value. Suppose if you will take 0.1, 0.1 whole square, what is that value? 0.1 is small value. So if you will take the square means 0.01. Okay, square of the smaller value is very small. That's why we can neglect the higher order terms, x square, x cube, x power 4, like that it will be there na. So we can neglect all higher order terms. So that's why only we can write here 1 minus x, 1 minus x. So in x means here exponential of e minus ef by kt. Okay, if you multiply minus inside means minus 1 plus this term. Okay, plus this term. Okay, now so how we are getting this term means here, so we are neglecting the higher order terms, because so compared to the this energy value, so t value is high, so that's why so this value will be small. That's why this value will be small means this total value will be small means so we can neglect the higher order terms. If we neglect the higher order terms means, so simply we can write this value into 1 minus x, 1 minus x. If you multiply inside the minus value means, so minus 1 plus x, x means nothing but here this term. Okay, now simply 1 minus f of e is equal to this one gets cancelled, remaining term is exponential of e minus ef by kt. Instead of 1 minus fe, we are substituting this value. Okay, so substitute the z of e value as well as 1 minus f of e value. Okay, z of e value is same, so only these terms will be changes. What is the effective energy will be there na? That effective energy is changes. Okay, so and 1 minus f of e value is simplified here. We are substituting these two value. Okay, further we will simplify this exponential equation. So for simplifying, so how to simplify means just follow the one trick. Whatever the here e minus ev minus e will be there, same that term should come here. So at that situation we can simplify this equation very easily. So that's why what we have to do for getting the like this term, what we have to do means we have to add and subtract with ev. We are adding with ev and subtracting with ev. Okay, now so what is the here e is the variable only, e is variable, so constant value is ef. That's why what I am doing means here, so minus ev minus ef, I am taking out, ev minus ef I am taking out, remaining term is e minus, okay, remaining term is here, so e minus ev will be present. Okay, e minus ev will be present. I am taking minus common here. If you will take minus common means ev minus e by kt, ev minus e by kt. Okay, if you simplify this equation, so did you understood here? Just we are doing here ev minus adding with ev and subtracting with ev. So what I am, which term I am writing out means, so here this one term will be there na. So this type of term I am keeping inside, so remaining other terms I am keeping outside. Okay, so like that, so I am simplifying this equation into minus infinity to ev into ev minus e whole power 1 by 2 into exponential of minus ev minus ev by kt into de. Okay, this is after simplification we got this equation. Same formula we applied here also. What we are doing means ev minus e equal to, we are taking, let us take x. Okay, now e is equal to ev minus x. Okay, so if we differentiate both sides, de is equal to, so here ev is constant. Means that this is the energy state of the highest energy state of the valency band. That's why this value is constant. Okay, de is equal to minus dx. So differentiation of constant value is 0. That's why so this will become vanishes. Okay, simply de is equal to minus dx. Okay, so and lower limit, upper limit. So here lower limit will become infinite, upper limit will become 0. Okay, if you substitute the lower limit here minus infinite, lower limit yeah, infinite only. Okay, if you substitute the those limit values, so infinite to 0, and here, yeah, so we are substituting the limits, and instead of EV minus E, I am substituting the X also. Yeah, okay, similarly here also I am substituting X. Okay, so this is same form. Previously whatever the form will be there, same type of form it will be. Okay, so for that, what is the simplification here? Integration of 0 to infinite, integration of, here minus dx is there, so remember here, so d is equal to minus dx. So if you that means send that minus outside, means what happened? So that integration limits will be changes, so that means upper limit will become lower limit, lower limit will become upper limit. If you remove the minus value here, limits will be changes, limits will be changes here. So previously this limits is minus infinity to 0. So if you remove the minus, means what happened? So that limit will be changes 0 to infinite, 0 to infinite. Now simplification of this equation. Similarly, so what is this? What is that? Pi power 1 by 2 into, so 2a by 2a power 3 by 2. Same I am substituting here. So pi power 1 by 2 into a power 3 by 2. A power 3 by 2 means, so a is here 1 by kt. 1 by kt means if you, that is in denominator. If it will come into numerator, means it will be kt. Okay, kt power 3 by 2. So just substitute that formula value, means, so we can get this value. We can get this value. Okay. If you simplify this equation, if you simplify this equation, similarly whatever we are doing previously, so same powers, whatever the same powers will be there, I am writing the same powers in one place. Okay, here pi into pi power 1 by 2, here pi power 3 by 2, and mh power 3 by 2, 2 power 3 by 2, and kt power 3 by 2. That all terms I am writing here, and simply here h cube will be there. H cube we can write into h square whole power 3 by 2. So that's why that all terms right I wrote here. Okay, remaining term is exponential of, I am taking minus common here, minus EF minus EV by KT. Okay, why I am taking minus here means, so here always it should be highest energy value. So this side or left side we have to keep highest energy value. So because compared to EV, EF value is the highest. EF value is highest. That's why I am writing here. So EF first. If you want to write the EF first, means I have to take the minus common here. Minus common. So minus EF minus EV by KT. So this equation gives the energy density of the holes. Density of, simply density of the holes in a conduction band. Conduction, sorry, valency band. So this is the density of the holes in a valency band. Okay, yeah. So this total term we can write into NV. NV is the here effective density of states. NV is the effective density of the states. Okay, so this total equation P is equal to NV into exponential of, so this whatever it will be there, that one. Okay, so if you know the one solution, either density of electrons or density of hole, so simply we can calculate the density of the holes also. Okay, so that means so both you have to solve. If you ask the question, means so both you have to write. So carrier concentration of intrinsic semiconductor, if they ask like that, means you have to write the density of the electrons as well as density of the holes. Okay, simply how to calculate the resultant carrier concentration. So in case of intrinsic semiconductor, number of holes is equal to number of electrons. Okay, that means density of electrons is equal to density of holes we can take now. That's why simply in case of intrinsic semiconductor, n equal to p. So that's why, so here n equal to p is equal to ni. Ni means number of charge carriers in case of intrinsic semiconductors. Intrinsic semiconductor. So that means simply that formula equal to ni square equal to n into p. N into p. Okay. So in case of intrinsic semiconductor, number of charge carriers ni square is equal to n into p. N is the density of the electron, p is the density of the holes. Okay, now ni is equal to under root of n into p. So if you substitute the n value in p value in this equation, n value and p value in this equation, already we solved n value and p value. If substitute this equation, means we can get ni value will be like this. Okay, same total terms will be same. What is the change above equation? This equation means, so me into mh whole power 3 by 2. Okay, and this value also. Previously e minus ec one term, so another one is ev minus e another term. So if you simplify that terms here, we can get ev minus ec by 2 kt. Okay, so if you simplify this equation here, ev minus ec is equal to eg. Okay, so this is about the carrier concentration in case of intrinsic semiconductors. Okay, yeah, so we will discuss briefly tomorrow again. So whatever the final equation of the intrinsic charge carriers and charge carriers in case of intrinsic semiconductors, we'll discuss tomorrow. So first of all, I am taking the attendance here. Today is 07 and okay. Any doubt on this? So just practice once. Without practice, you could not understood this equation. So practice is important. Practice is important. So just practice. Already in your book it will be there. So just see the book and practice it. So then you will understood. If you will get again means, so then you ask me. So just read once. So this also very important question. Very important question in second unit. So these carrier concentration, intrinsic, in case of intrinsic semiconductor as well as extrinsic semiconductor, this carrier concentration is very important. Okay, if you have any doubt means you can ask, otherwise you can leave.